Yeah.
Okay. Good morning or good evening to everyone, depending on which time zone. I'm the new committee member for the WISE webinar, and I'm glad to announce this webinar on waves and CIs. Today we have two speakers, Jean Rabault from Norwegian Meteorological Institute and Luke Bennetts from the University of Melbourne. So I'll introduce briefly Jean, which is been working at the Norwegian Meteorological Office since 2020. He completed his PhD at the University of Oslo on fluid dynamics and oceanography. And most of us know his work on the OpenMet buoys, a low-cost open source buoy design that he deploys in cluster to study, to have a better understanding of the physical processes in the marginal ice zone. I'll leave the floor to Jean for his story.
Yes, so thank you very much for the kind introduction and the invitation. It is very nice, this WISE Zoominar, very exciting concept. Today I'm going to talk about waves in ice and present a bit which kind of large data set we've been gathering with our low-cost buoys and a bit how we use them. Before I start, I want to say that today I'm presenting, but really what I'm going to talk about today is a result of work with many colleagues over many years, started in 2015. And also I will keep the presentation quite general because I thought about this a bit when I prepared the presentation, like either I deep dive into one specific application or case, or I go quite broad to give an overview of what we do. So I went for the latest, and we can always have in-depth discussions about specific cases if needed. So, okay, why gather more data in the marginal ice zone? Of course, we all know that the marginal ice zone is a very complex and challenging area. I mean, we all know about this kind of aspects with variety of ice types and conditions, the two-way coupling between the waves and the sea ice. And I think that it's emphasized regularly in the literature, but we can even emphasize more that it's an area that is challenging to measure, and instruments have statistically very short lifetime. So actually you have quite a few trajectory deep in the Arctic, for example, but in the marginal ice zone, like instruments are usually there only for a few weeks or months at most before either they leave it or they get destroyed. So I think that we actually have data sets that are quite partial and not fully statistically representative yet. And I think it's also fair to say that it's an area where theories and models do not work so well. I mean, I think that there are a number of ground truth questions that are not completely clear. And as we all know, like for example, parameterization for the wave attenuation in the sea ice, you can get something to work based on curve fit or parameter tuning, but it's very difficult to get there from a first principle approach. So I think that I started working on this in 2015, and originally I think my PhD was supposed to be more about like theory and laboratory work. But really, after working a few months on this, I really got the feeling that the point where we need to focus in order to advance this is rather the data collection and having data sets that are representative of the wide range of conditions that can be encountered. And this is really the motivation for the OpenMet buoy and all the projects that have been related to this. Yeah, so this is just to illustrate, I mean, why I really think that we need this better sampling of the marginalized zone. Oh, sorry, I see translation enabled. Yeah, okay. You can see on the left, it's just a snapshot from a website of the Norwegian Polar Institute that shows the AIBP and NSIDC data points for summer in 2018. And you see on the right a comparison of the kind of sampling we can achieve by using our low-cost OpenMet buoys. So you can see there are quite a few buoys in the Arctic, but few of them are in the marginal ice zone. And by contrast, we can really focus on like peppering the marginal ice zone with buoys. So a few words about deployment opportunities. Our methodologies are typically we deploy from ships, and we like to make array of buoys starting from the start of the marginal ice zone and extending deeper into the ice. Very, very classical thing. I think what is a bit unusual about our deployment methodology is that we usually try to deploy several tens of buoys at once. In some cases, up to around 40 buoys for a single deployment. And we are very lucky at, in particular, the Norwegian Meteorological Institute to have a lot of project and collaboration with other institutions in Norway. So, for example, I'm going to talk about the deployments we've had from the research vessel Kronpris Haakon, the Norwegian Polar Institute icebreaker, in 2018, 2021. And now we also have more and more collaboration with the Norwegian Coast Guard. So we have already had 3 deployments from the Norwegian Coast Guard KV Svalbard over the last 3 years. And in addition, if I will talk about this a bit later, but when we manage to have enough resources, we're also happy to provide buoys for free to other groups to deploy. Yeah. So, for example, there are some buoys that we have given to the Odin expedition this summer 2025. A few words about how we operate. So usually we operate directly from the ship. We have not used helicopters so far, and we just have the ship to stop and to put it on the ice, either using on the research vessel Compression Con, we use this big arm, and on the Coast Guard they have a fast release for rescue ships, so we can go on the ice quite quickly. Okay, so a few words about the OMB design. I mean, the core design of the OpenMed buoy, the idea was to make it as low cost and nimble and effective as possible. So it's actually just a box 12 by 12 by 10 centimeters, about under 1 kilo, maybe 850 grams. And we get autonomy with 3 lithium batteries of about 6.5 months or over it without solar panel. And actually, the OpenMade buoy as we use it today, it's like the second plus generation in a sense, because we have the OpenMade buoy version 2021, which is this one. Before it, we had an OpenMade buoy that was much heavier and more power hungry, which was the version 2018. And even before it, we had actually stuff that was pure loggers without iridium connection. And really, this has developed over the years with an idea of having like fast iteration and cost optimization, and to leverage advances in other fields, in particular electronics. I mean, over the last 10 years, I think I can get a motion sensor that's about 50 times cheaper than what it used to be to do the same measurements. And by moving from traditional embedded Linux to purely microcontroller, I got a power saving about a factor of 1,000. And in addition, we have the rise of those open source communities that make development much easier. So I think this is really one thing I'm very excited about, is when I see a potential for a 10 times or more improvement. That's a bit what I'm hunting for. And sometimes it's not really in oceanography or in waves in ice science per se, but it's something we can leverage for it. And so we build this ourselves purely in-house. So we have full control over the design, we can customize, and we make it also available for other groups to customize. So for example, this spring I've built about 50 of these buoys. It's about a couple of weeks, 3 weeks maybe, because we have quite a few extra sensors now on them of work that I do by hand. If we look a bit at the core features, we have global connectivity with Iridium, we have two-way communication. It's power efficient enough that we need no solar panel. On previous version, we had solar panel, and it's always a mess to keep them working on the ice. It's fine in every temperature. It has been used by -40 in the Antarctic. Of course, for position, we use GPS. For wave measurement, we use an accelerometer. So we have all signal processing chains that go from the 800 Hertz sensor through the Kalman filtering through a 10 Hertz wave data buffer, and then we do Welch transform on it, basically. And nowadays, more and more, we use also temperature sensors to measure the air temperature, the snow surface temperature with some infrared measurement, and the sea ice profile. So we're coming closer and closer to something that looks a bit like a Simba, I think. We're still in the process of making all of this more robust and documented, but I think we will publish technical blueprints about it quite soon. And really, I think the nice thing is that we can cut the cost to about $700 all included for a standard OpenMed buoy, and we pay per month about a bit over $100 for the Iridium fee, and we could reduce it by tuning how much communication data we send. So I think if you compare with commercial buoys, that can be typically, I don't know, maybe nowadays, if you really know the right company, you can get something cheaper. But historically, maybe the cheapest one have been about $8,000 per piece. Then we are well 10 times cheaper, which is why we can get 40 buoys deployed instead of 5 or 6. And as I was saying, we are putting more and more sensors on this. So those are pictures from buoys we have been deploying from the Norwegian Coast Guard recently. So all of this is homemade and low cost. So it's basically 3 shafts for cleaning broomsticks together with 3D printed, custom printed tripods. So all of those assemblies cost just a few tens of US dollars actually. And but we still have a good radiation shield for the air temperature. Now we've iterated about it. We have an IR sensor that is actually a medical grade sensor that we use to look at the snow surface temperature, and we have found ways to have low cost temperature measurement string. So we pay about 150 US dollar for a string with 26 measurement positions, which is, I think, very competitive. So all of this is going to be documented over the next few months and everything made available as usual. And I think that it's fair to say that we have had a certain degree of success with the OpenMed buoy. At least buoys that I know of that have been deployed, we are above 500 now, I think. So we have been producing a lot of them at the Norwegian Meteorological Institute and also a number of universities, also our friends in Melbourne and Tokyo. The Danish Meteorological Institute have been using some, Chalmers in Sweden, and there are probably more that I don't know. So I think this illustrates very much the fact that, okay, it's purely something that is technical, but it still has quite a bit of impact because it really makes all the scale of deployment possible. Okay, so if I go a bit through examples of deployments and datasets, being very quick, we had, for example, those deployments southeast of Svalbard. We actually have a paper discussing some of this data. I will come back to it. So here you can see typically the kind of deployment we do, right? We go into the marginalized zone, we put buoys at regular intervals, and then some of them live long, some of them live short because marginalized zone is a very violent place, and we just get the trajectories as they drift, of course. We have also had, this is not deployment I was making, this is a group at University of Tokyo, so Takehiko Nose, Takuji Waseda, Tsubasa Kodaira, and all their Japanese Antarctic Research Expedition program. But I like this slide here because it illustrates that the OpenMed buoy can also live for a long time. So this is a trajectory, for example, for a buoy that was lucky not to get crushed over the first melt season, and then it lived for a full year, drifted above 5,000 kilometers, had a transmission time of nearly 1 year. And we have the link to the paper here, but some fun measurements where you could really see waves that had been propagating from an extratropical cyclone for like 800 plus kilometers into the sea ice. This is a map I showed. So I like this one too because it illustrates like the kind of volumes of data we can gather. So this is actually a summary of all the buoys we've been deploying around Svalbard during the year 2022 alone. And this is both buoys from the Norwegian Meteorological Institute, University of Tromsø, and some buoys deployed in collaboration between UIO and some private individuals, and some buoys deployed in collaboration between the Alfred Wegener Institute and University of Tokyo. So you see, we can really get a dense data set that gives a unique view about the marginalized zone. And then there was those campaigns I was mentioning that are starting to happen regularly from the Norwegian Coast Guard. So we had the first one in 2024, spring 2024. We just got the paper, the data release paper, accepted and published, and the data have already been available for about half a year. So you can go there if you want. And what is new now is that this is in collaboration also with people interested in the atmosphere. So we have all these temperature measurements, and this is used both by us doing waves and sea ice drift, but also by our colleagues doing looking at atmospheric gradients into the marginalized zone. So yeah. We are the same kind of expedition now again in April, May, where we put again 25 buoys. So we're still working on quality controlling the data, and hopefully this will soon be out. And by the way, you can see in the link here that actually I'm linking to this very nice Ocean Virtual Laboratory from our friend at ODL. So that's the nice thing also with open source, is that it makes it very easy to interface all those systems together. So basically we split data in a standard format, and then they can just integrate it into their portal. And the portal is extremely well built and very nice for visualization. Also, when we deploy the buoys, so we know which flow we put the buoy on, and yeah, it helps really to improve the quality of the deployment. And I really invite you now, I'm trying to put the links systematically in the paper and always use this for the visualization. I really invite you to click on those links and then play around in their data visualization portal, because it's a very good way to visualize SAR images and buoy data and wave and quantities you want. So I think that's another thing I'm very excited about, is in addition to purely the wave measurements, also and the buoy measurements, also to make the visualization better and better alongside other sources of data. And this is what we get by making this open and collaborating with OVL folk. And now we just had actually the first deployment that we were involved in very deep into the sea ice. So it's still an ongoing deployment and data ticking in, but basically putting buoys up to 89° north. So it's a bit new for us. So we're going to learn quite a bit about how to robustify the buoys to the melt pond and this kind of stuff. So a bit less focus maybe on the marginalized zone, but we're very excited about those sea ice temperature profiles. So yeah, more to come. And yeah, of course, I think we have seen these figures. Typically, what we send regarding waves is those one-dimensional spectra. So yeah, here are a few examples from the SFAL MIZ24, so the deployment we had last year during the spring. And yeah, more data are coming. Typically, we can get invited to 2 to 5 cruises a year. We try to make the data available within big O of 6 months. And the limiting factor for us is actually the funding for the buoys plus a bit of traveling money. So we are very lucky to have good access to ship times, and usually for free or nearly for free. So by the way, this is one of the things, it's a bit frustrating sometimes. I have some project applications that get rejected because we didn't have a clear budget for the cost of having access to the ship. But then in the project application, it's written, we get the ship access for free. So when we say it, please trust us, we do get ship access for free. Yeah, and of course, in order to convince people to release the data and make everything citable and make the bean counting part of the systems happy, we are using a lot those open source data release papers. It means it's a bit chaotic because then you end up with a million different data sets, but we have an overview of where this is released. So I invite you to go to this GitHub webpage if you want an overview of all our data. And we are very happy to list to data from other groups too. So if you have data that is a bit hard to find, feel free to open a GitHub issue or pull request. And yeah, because I think we end up nowadays with a lot of paper stating data are released at this URL, and those URL are scattered all over the internet. So just having a simple index to find them, I think, is already useful. Okay, so what science do we do with the data? That very quickly in a few minutes. Of course, I'm working at the Norwegian Meteorological Institute, so it's an operational institute. So our main role and reason to be here is to focus on what our users need. So then we do a lot of model parameterization tests and development, and use those data to gain trust in model and put them in operational use. Also, this is used by colleagues who do sea ice drift study and this kind of stuff for everything from weather, climate, search and rescue, this kind of stuff. And I think that for this kind of purpose of operationalization, our data are used quite a bit, both at the Meteorological Institute, ECMWF, Meteo France, Naval Research Laboratory, and probably more. Yeah, I think expect some news this fall. I think we are going to see more and more operational models taking waves in ice into their model continuously. But of course, the nice thing we like to do with those data is to have this double approach, right? That we deliver what our institute wants and what we get the money for, which is serving our users, but also those data have some scientific value. So we also try to do some science with it. And I like this slide. It's a slide from a paper by Joey Vormans et al., because it illustrates a lot of the mentality and motivation for the OpenMet buoy, which is like fill the plots with clouds of data, because the sea ice conditions can be so specific and the wave condition and weather condition so specific that if you take one deployment alone, at least when I work with the data from wave deployment alone, I usually feel very worried to overfit to this deployment and to see ghosts in my data and overinterpret. So for me, what feels really important is to have large data sets that can get as statistically representative as possible. And then I think you have a better chance to see robust pattern emerging. And I think it's true, of course, we all know this in everything wave and oceanography related, but I think it's especially true into the marginal eye zone and waves in ice community, where we are very data limited and we have a huge range of conditions that can happen. So this is an illustration of this. Like if you look at one individual data set, it's very difficult to see a pattern. But if you group, as Joey has done, all data he could get his hand on back in 2020, I think, or 2020, and you look at the sea ice breaking or non-breaking states compared to different non-dimensional parameters, I think you can start to see some patterns emerging. We have also had some fun data sets coming now and then, just thanks to serendipity, because we just put so many buoys that sometimes we are just lucky and we get one back. So we just got a paper accepted, which is like buoys of the old models that had SD cards storing all the data. And then one of them got stranded in Iceland and was recovered, and we got access to the raw data. So we had a lot of fun looking at non-Gaussian data points in those data sets and trying to relate it to flow-flow interaction and maybe even collision. So yeah, that's another thing that when you put so many buoys, we're always told you should not have a research project or a field campaign that is a fishing experiment when you just randomly drop stuff and hope that you get something exciting. And I agree with this, but we should have a clear, robust goal when we do field work. But still, it's nice that as a byproduct of having so many buoys, we actually got this fishing expedition effect, in a sense, in our data. We also have another example of this kind of stuff is by having so many buoys, we were able to observe, for example, complex attenuation dynamics. So this is from, we have also a preprint about this. Those very weird spectra. Initially, I even thought it was a problem with my instruments, but actually we can show that there are those puffs of wave activity and wave damping and wave activity and wave damping, and we can relate it to the local state of convergence and divergence of the sea ice. So if you're curious, we have the preprints there. So I think this is also an illustration of something we only observe because we have so many buoys, so we can really sample also weird conditions and try to understand something about the physics based on it. Recently, another example of this kind of effect of having many buoys is we have just released a preprint about harmonics peaks in the wave spectra. So I've been aware of this since 2015, actually, that in some of the data we see a harmonic 2F peak. And actually this matches with the bicoherence peak when we look at the raw signal. But I only had it in one data set, maybe a couple of data sets, but over the last few years, actually, we've been able, you can see this at the bottom, to observe this in a very wide range of open-made buoy deployments. And it's not here systematically, so it's not a noise or an error on the sensor, we believe. But we can relate it in particular in the cases where we get the full wave data. We're able to relate it to elastic part of the dispersion relation playing a role, and we're able to show that it can match actually some triad wave interactions that are expected. So I think more data is needed here to be completely conclusive, but still the fact of going from one data point I had in 2015 to now thousands, even tens of thousands, I think we are about 50,000 spectra. It allows us to get the representativity we need to start to dare to talk about it and show that this seems to be something that is happening regularly. Okay, so in conclusion, way further, more data are in the pipelines. You can follow this GitHub repository where we put links to all the different data sets. We're always looking for more buoy funding. Buoy funding and a bit of travel money is our limiting factor. There is nothing that tells that we couldn't deploy several hundreds of buoys a year if we are able to manage to scale this up. We're working on getting operational models to take into account waves in ice, and we're also using this data as a nice side effect to revisit scientific questions with big data sets that we hope are representative. And of course, we also have still a technical deployment. We are considering now doing redesign of the buoys, try still to cut the cost by a factor of 2, try to go beyond the 1D spectra that we send to continue to scale up. Yeah.
Thank you very much, Jean, and very nice presentation. I'll open the floor to questions. Does anyone have any question for Jean? We have 4 minutes for questions at this stage.
I'm happy to ask a question if no one else is going to, Alberto.
Yeah, go for it, Luke.
Hey, Sean. Really nice talk and great stuff. Yeah, good to see you. Do you ever put the buoys on fast ice?
So we were doing quite a bit of fast ice initially. For example, those that are here are from fast ice. But this was originally because we didn't have some good telemetry and iridium communication and so on. So nowadays we're mostly focusing on the marginalized zone because I think it's more relevant for our institute. But I know that, for example, Joey and Joey Vormans and also all the group around Takuji Waseda, they do put buoys onto fast ice. So it's perfectly possible. I think if you put on fast ice and you know that you can revisit, then I would go for some of the a bit older model of buoys or even the pure loggers. Basically, today we can build something that is just a logger giving you the raw time series data. We can build it for maybe 150, $200 per logger. So we are actually having some hopes, some diffuse ideas of maybe one day having a project and building 200 of those loggers and distributing them on a big landfast ice sheet and recovering all the raw data that we couldn't recover over Iridium, maybe to get a 3D motion of the landfast ice. But it's a bit less relevant for the institute where I'm working nowadays.
Okay, sure, I understand. But yeah, I think it's a really good idea that was proposed some years ago to sort of simplify the scientific questions to look at what's going on land fast ice, and also more achievable to get a really good spread of the land fast ice in a particular region, let's say. Anyway, just an idea.
I think it's a good point. I would love to do a bit more work again on landfast ice. There is a question, though, that is the condition on the landfast ice are very different from the condition you observe in the marginalized zone, right? I mean, it's, for example, at least in the Norwegian fjords, I know landfast ice can be a very nice and continuous sheet. And it's not something that you see very often from an icebreaker in the southern Barents Sea. So maybe you may be observing different regimes too a bit.
Oh, absolutely. I mean, you can't take the findings on fast ice and directly carry them over to marginal ice. At least I don't think you can. However, it might help our understanding of what's going on in the marginal ice. So,
yes, I think this is an interesting question, right? Because it may be that the dominating mechanisms are different in the landfast ice and the marginalized zone. And then it may be that it's difficult to transfer knowledge, actually. Let's say in one case, you have a very nice continuous sheet and you have maybe the elastic effect are important. And the other case, you have small broken ice flows and then there are basically no elastic effects. That's
sure, yes, we have that understanding. We shouldn't make that judgment call. I should let someone else ask you a question.
Yeah, I have just a quick question before we move on to Luke. And so I think you quickly touched on it. At the moment, it's only one directional. Is that correct?
Yes, it's correct. So, I think this directional question is really tough from buoys in situ because there have been a lot of use by GPS buoys. Then with the Doppler velocity, you get the horizontal velocity and you get the 2D directional spectrum. But if you get deep into the ice enough, the horizontal motion gets really, really little and it's difficult to get good. I find it sometimes a bit difficult to get good confidence. An alternative is to use a magnetometer to know the direction of the north, but in the polar region, in particular in the Arctic, it's nearly vertical. So how good do you trust the magnetometer reading that you get? A third way is to get a Kalman filter that it's everything together, but then you combine all the issues. A fourth way would be to deploy an array of buoy, and we have been doing this in the past and doing like cross correlation analysis kind. But then the problem is that you know the orientation of your array when you deploy it. But if you're not on those fast ties and if stuff moves, so I think it's a really challenging thing. We have some ideas about it, but more work is needed.
Okay, I'll cut you short because I don't want to overrun, and we should move to Luke. But thank you very much for your nice presentation. Luke, if you can put up your presentation. So Luke recently moved to the University of Melbourne, where he's a professor now, after having spent a few years in Adelaide. His research focuses on ocean wave interaction with ice flows in Antarctic marginalized zone, so mostly to the south, with broader implication in Antarctic and Southern Ocean science. He led a philosophical transaction 8 issue on the marginalized zone dynamics and reviews of geophysics on multi-scale Southern Ocean dynamics in 2024. And is chair of the Causewaves, which is closely related to the WISE meeting, which more mathematical, and is going to talk to us about defining the marginalized zone and analyzing, apparently.
Yeah, thanks Alberto for that introduction, and thanks for the invitation, and thanks everyone for coming along to listen to me talk for the next 20 minutes or so. Yes, I caught Alberto out a bit there because I did extend my title a little bit by putting in the "and analysing," which is fairly obvious why I did that, and will become even more obvious during the talk. Look, this is work with a lot of collaborators. I want to highlight in particular Noah Day, who is my former student and will be my postdoc as of Monday next week, and Alex Fraser, who's a collaborator down in Hobart. So the talk is, well, it's the first few slides, which are by me, which are really going to be me rambling on about my thoughts on the area, and hopefully not getting into ranting about the area. And then I have taken slides from Noah and slides from Alex and combine them all together to give the overall talk. So look, I was going to show you this really beautiful movie by my colleague Alessandro Toffoli, probably a lot of you know already. So it was taken on the South African icebreaker some years ago, 2017, I think Alberto was probably there as well. And it was going to show you the Antarctic marginal ice zones, typical conditions during that time of the year. And the important things were going to be that the marginal ice zone is dominated by these small flows that we refer to as pancakes, about 3 meters in diameter, separated by frazzle. And also that there are large waves present in this region. So the icebreaker is over 40 kilometers from the ice edge. Nevertheless, the significant wave heights, which are in the movie, are around 5 meters. However, testing earlier, I've been optimistic about the movie working over Zoom, so I think I might just skip over that, the horrible, awkward jerkiness. And you can ask me to show it in the question time if we've got nothing else to talk about. So the key thing is that when we talk about the marginal ice zone, we are talking about ocean wave interactions with sea ice, in particular with sea ice flows. And in fact, this is encapsulated by a quote from one of the godfathers of the field, Peter Wadhams, from 30-ish years ago. So he described the marginal ice zone as that part of the ice cover close enough to the open ocean boundary to be affected by its presence. And he's not saying it here, I put it in square brackets, but everyone takes it to mean that he's talking about ocean waves. And people often refer to this as a definition of the marginal ice zone. However, I don't like to do that because it's not a definition that you can actually go and use in any meaningful way. It's more sort of a characterization of what the marginal ice zone is. So here is a schematic that comes from a review paper that I led last year. It's trying to show some of the key processes that are going on in the marginal ice zone, again, with a focus on the Antarctic marginal ice zone. So the schematic is showing the marginal ice zone, and I'm imagining that out to the right-hand side, we have the open ocean, and we have waves coming in from there, traveling into the marginal ice zone. Then out on the left-hand side, we have no more waves, and we have what I refer to as the interior ice pack. Then I feel compelled to give a spatial scale to the width of the marginal ice zone. So, I mean, I kind of dislike doing this, but if you really press me on it, then I would say it's around 200 kilometers in the Antarctic. So I just don't want you to get misled by the smaller scales that I'm highlighting in the schematic there. So there are two broad things going on here. First is that the waves in the marginal ice zone are impacting the ice cover, and they do this in a number of ways. If we start out on the left-hand side, we have breakup of the larger ice flows towards the interior ice pack by the waves. We then have wave-induced drift, which is much stronger because of the flows being broken. The smaller flows, they melt more readily because of the greater perimeter versus the area of the flows. We have the overwash process, which is where the waves go over the surface of the ice and they remove the snow cover. We then have the smaller flows out towards the ice edge being herded and rafted by the waves, and also these collisions occurring that Jean was referring to earlier. So there's a lot going on. The breakup is the one that's been the main focus. There's also something I'm not showing very well in the schematic, which is the promotion of the growth of pancakes due to the presence of the waves and the turbulence that they cause in the water column. So we'll take that into account. But then there's all these other things. And there's a really good paper that is on the cryosphere discussions led by Rob Masson, which opens up many new directions in the impact of the waves on the ice cover. Then the other side to the coin is that the ice cover attenuates the waves. So it's generally considered to be exponential over distance. That limits the distance that the waves can impact the ice cover. The other key part of this is the ice cover acts as a low-pass filter, which means that the shorter waves are getting removed closer to the ice edge. So now we go to a broader scale. And people care about marginal ice and wave ice interactions for a few reasons, but one of the most cited is because of this potential positive feedback loop, which connects with the warming temperatures we have around the world. So imagine that the ice cover becomes weakened for some reason, probably because of the warming temperatures. Now, that is going to allow the waves to penetrate farther into the ice cover. And that's going to allow the waves to impact the ice cover over greater distances. Generally speaking, the impacts of the waves weaken at the ice cover. So that will allow the waves to travel even farther, impact more of the ice cover, and so on and so forth. So this was the underlying concept behind some results which were published in a Nature paper by Alison Cahoot and co-authors in 2014. I'm showing some of the key results from that paper, which have been cited many, many times since then. So the blue curves are showing the trend in the significant wave height close to the Antarctic sea ice edge. The results are split into the summer, the ice decay season on the top, and the winter ice growth season on the bottom. Then the red curves are showing trends in the location of the ice edge. And this is done over each longitude, and it's done over a period of a few decades or so using various data sets. And what you see is a really strong correlation between the trends in the waves and in the location of the ice edge. And just note that the trends in the waves is flipped. So it's going from positive on the bottom to negative on the top. So this is saying that increasing trends in waves mean decreasing trends in the ice edge and vice versa. Okay, so that provides some connection between the wave-ice interactions and larger scale responses of the ice cover. However, the results have not been confirmed independently or refuted here. It simply hasn't been touched again. And that was back in 2014. And there has been a lot going on with the Antarctic sea ice cover since 2014. This stuff desperately needs to be revisited. So that paper, those results, and some others around a decade or so ago really drove a lot of activity on the marginal ice and wave ice interactions. And we're now at the point where we have a community, an international community, and we have our own meetings, and we have our own debates within the community, and we have wise Zoominar sessions and so on and so forth. And the issue of Filtrans that Alberto referred to in my introduction. And there's a lot going on in all of the subfields of marginal ice as well, covering theory, physical models, numerical modeling, observations like in John's talk, and often centering around these large campaigns driven by the US Office of Naval Research and others. But before we get too carried away with all of the activity that's going on about the marginal ice zone, I think it's important that we think more broadly about how other people from outside are viewing the work that we're doing. Now, if you're like me, you avidly read the IPCC reports. And when the last report came out, I do what I usually do. I jump to it and I go to the cryosphere section, then I go to the Antarctic sea ice section, and I go looking for relevant stuff. And the last time I did it, so this is back in 2021, this is what I found, right? I'm highlighting down here. My first thought was brilliant. They're talking about wave ice interactions. But then I thought more carefully about it. What they say is that the broader implications of wave ice interactions are unclear because we just don't know enough about it at this point in time. That is how people from the outside see us at the moment. So I think it's very important that we keep that in mind and that we aim to connect what we're doing in our research on the marginal ice zone, wave ice interactions, to that bigger picture, whether it be the climate, Antarctic sea ice retreats, or whatever you think is important. But before we do that, we need to be able to define the marginal ice zone so that we can tell people why it's important. And then I've got this, what I think is a great quote by my mentor during my postdoc years, Vernon Squire, another godfather of the field. So he says, it probably seems remarkable that there's so much been going on in the marginal ice zone over 40 years or so. But as a community, we still can't decide on the definition of the marginal ice zone. So for a long time, there was an ice concentration definition that was used. It was really done just for convenience. So there's this band of ice concentrations, and that's where people said the marginal ice zone was. So it's good because it's simple, because ice concentration is often known. But the problem is that it really doesn't match the way Wadham's described it or how anyone in the marginal ice zone community sees the marginal ice zone. Well, recently, we have moved to wave-based definitions. So I'm highlighting here some work that was done with laser altimeters in a paper that Alex Fraser was involved with, and also Alberto. So they have the laser altimeters, which are flying across the sky and basically use snapshots of the elevations in the ocean surface and in the sea ice cover. And then they can take these and they can identify this region where they see wave attenuation, okay? And they use that to define the marginal ice zone. So I think this is fantastic. The only thing that I would point out about it is that it doesn't tell you whether the waves are often in that region because it's just a snapshot. And then there are the flow size based definitions which have been proposed. So Danny Dumont from Quebec has been one of the people who's been pushing this idea. And here is what he sketched on a satellite image. So here he's trying to define the difference between, or the boundary between the marginal ice zone and the inner ice pack. So the large ice flows from the inner ice pack, and the marginal ice zone, they're so small they don't get picked up by the satellite. Really, we haven't had the capabilities to make the most of that idea up to this point. So just a quick run through the basics of wave attenuation. Jean already gave a good introduction to it. Look, I feel compelled to refer to attenuation due to scattering and dissipation. We love to debate that in the marginal ice zone community, but really the problem is we don't know what is causing the dissipation. As I said earlier, we do have pretty good confidence that the attenuation is exponential over distance. So this is often what we do. We take the energy at some location X into the ice cover, and we define it to be the energy of the waves at the edge multiplied by some exponential, where alpha, the coefficient there, is what we refer to as the attenuation coefficient. So we know that alpha is frequency dependent because of that low pass filter property that I referred to earlier. And based on observations, we know that it obeys a power law. So here are some observations, right? Each data point is the average of a lot of underlying data, and we're plotting versus the angular frequency. Okay, so this is the Ki, which is the attenuation of the amplitude rather than the energy. But you just need to multiply it by 2 to get to alpha. Okay, and so we fit curves through this, as Jean was saying earlier, and we decide that there's a power law dependence, which is about an exponent of 3, or we can write it as a quadratic plus a power 4 term like that. What we don't know is really anything about the way that the attenuation depends on the properties of the ice cover. That's ongoing work, but I think it's going to take a long time until we really understand that. And so in the meantime, we're sort of pushing forward in trying to make the most of what we do know about wave attenuation. So I was involved in a project many years ago to construct a wave ice interaction model. And what it takes into account is both the attenuation, and it does that by putting an ice source term into the transport equation that you're probably all familiar with in wave models. So that source term gives the attenuation, an exponential attenuation. It has to depend on frequency in the way that I've outlined. It should also depend on the properties of the ice cover. But at this point in time, really, it only ever depends on the concentration in a very simple manner. And then there is a wave-induced ice breaking part, and we do that in terms of some tolerance on the strains on the ice cover, depending on their amplitude and wavelengths. And so we have ways of calculating what we call a significant strain based on the wave spectrum at a particular point in the ice cover. So this wave ice interaction model has been used in wave models, it's used in sea ice models, and it's also used in couple models. Really, it should be used in couple models, but often we're constrained in what we can do. And so we just have a sea ice model with a simple wave component or a wave model with a simple sea ice component. So I come from the wave side, and there have been developments on the sea ice models over the past decade as well. So standard sea ice model involves a sea ice thickness distribution according to this balance law here. So we have some advection, we have a thermodynamics term, and we have some mechanical redistribution, which in the classic model is just from ridging. But then there was this joint flow size and thickness distribution model proposed, which has started to go into sea ice models. So we have a more complicated evolution equation, so it's now in flow size and thickness space, and we have wave ice interactions built into it. So it comes into a wave breakup term, and it also comes in the thermodynamics term in the way that the waves promote the growth of pancakes. The most important thing is this now allows us to identify a marginal ice zone in sea ice models because we have the flow size parameter in there. So we've taken this idea in the size 6 sea ice model, and we have put in a simple wave module into it. So the wave module takes the wave energy at the ice edge based on wave hindcast, and then it attenuates the wave energy over straight line meridional transects into the ice cover, attenuating according to one of those power laws that I described earlier. But then that wave energy in the ice cover activates those different processes in the sea ice model, the breakup and the growth of pancakes. So we then ran this model at 1 degree over 10 years in an otherwise standalone sea ice model. And what we did is we decided that we wanted to be able to identify the marginal ice zone for what we describe as snapshots of the ice cover given by the outputs of the sea ice model. And to do that, we use this K-means clustering algorithm. And so we put into that 5 sea ice variables, and these 5 variables came after a lot of testing to get it down to the core variables. And we got the K-means clustering to tell us what the natural clusters are of the sea ice data when we tell it how many K clusters we want. So here are some snapshots of what it gives us. The different colors are the different clusters given to us by the algorithm. And we're going between K is equal to 2, 3, and 4 different clusters. And what we want is for that red region, the outer one, to be the marginal ice zone. And in order to determine how many clusters we should use, we had a wave heuristic in which we looked at the statistics of the wave heights at the interior of the red region, okay? And from that, we decided that if we chose K is equal to 3 clusters, then we just occasionally get large waves reaching the interior of the marginal ice zone, which we think is consistent with the Wadham's definition. So we ran with that. And here I'm showing you the evolution of the areas of those 3 clusters where remember that the red one is the marginal ice zone over a given year. And what you see is the marginal ice zone, whilst it's often one of the smaller of the 3 regions in terms of the area, it's still a significant proportion of the ice cover. We then compared our measurements, our model outputs for the marginal ice zone with some of those our laser altimeter measurements that I referred to earlier. So our model is the red, the laser altimeter is the green, and then the gray is coming from the concentration definition. And what we see is not perfect agreement, but really very good. And then if we take the flow size variable out of our clustering algorithm, then we get the purple. And that's just collapsing down to the sea ice concentration definition. So that's telling us that flow size is incredibly important when you're defining the marginal ice zone based on the ice cover properties. We then proceeded to do analysis of the properties of the marginal ice zone. At the top here, I'm showing you the rate of wave-induced breakup. So the red is the marginal ice zone, and the gray is the interior ice cover. So there's 2 other clusters put together. And clearly the breakup of the marginal ice zone dominates across the year, except for during the winter, which is when the marginal ice zone is dominated by those small pancakes, and they're too small to be broken by the waves. So everything basically goes to 0 there. Running out of time, Alberto, am I? We then looked at the ice speed. The marginal ice zone is consistently greater than the interior ice cover, particularly during the spring. So that's down to a combination of the strong winds at that time of year and also a decrease in the ice strength. And we looked at the melt rates. Melt rates are much greater in the marginal ice zone than they are in the interior ice cover. Well, part of that is because the marginal ice zone is farther north, so the temperatures are warmer, but it's also down to the flow sizes being smaller and hence the lateral melt being greater. Now, I'm running out of time, so I'm not going to go through too much of the second part of the talk, which was only a few slides, which is how we can get the marginal ice zone over multiple years using radar altimeters. And this is work that was led by Alex Fraser based on an old paper that Chris Horvat and he found in which they proposed someone proposed the idea. So all I'm going to show you for the sake of time is that if we take the width of the marginal ice zone that comes from the radar altimeters, for which we can go all the way around the Antarctic and construct an average, and we do something similar with our model outputs, then we get this almost unbelievable agreement between the two data sets. Now, I don't want to overstate things here because there is some tuning that has to be done. But given the simplicity of the model, given the fact that it's in standalone, given that this is the first time that we've done it, it is very, very motivating to have this agreement. Okay, so for the sake of time, to get a few questions, I don't think I really need to go through my concluding points here. So I might just stop at this point and then allow a couple of minutes for a question or two.
Yeah, thanks, Lou, for a nice presentation. If we have any questions at this stage.
If not, I can promote the next COS waves. I'm sure you all want to come to Australia when it's the middle of winter in Europe and nice and sunny here. So we have COS waves at the end of January next year. There's a lot of people interested in water waves who go to COS waves. So please do visit the website and consider submitting an abstract and coming along.
If no one has a question, I have a quick one, look, and it's mostly fundamental, also to Jean maybe. So the framework is with an exponential attenuation alpha, which, I don't know, some models say is function of the thickness. So in reality, that alpha is space dependent. So it's an alpha of x. So the attenuation rate might not be exponential. I mean, the profile might not be exponential.
Sure. Yeah, but I very much agree with what Jean said earlier, which is that you have to consider things in a statistical manner. And also you need to think about the question that you're trying to answer here. No question in my mind that the attenuation that we've put into the model is correct. It's not. I mean, you know, it's wrong. But on average, it's probably okay. There's quite a lot to say that it's okay. So if we do enough averaging of the outputs, then probably we're doing okay as well. And that's the indication that we have. But there are, as you well know, Alberto, there are fundamental questions about how the attenuation changes in response to the ice cover and winds and currents and other things. Sean, did you want to comment?
I don't know if I can add a little comment.
You're muted, John.
If I can add a comment on that, though, before John jumps in. I mean, if you average and average and average, it's probably good at large time scales, so like climate prediction. It's probably not good for operational prediction that maybe at the Met-No are very interested in.
Do you want to respond, Sean? That's probably directed at you. I agree.
So what you mean is that there may be different scales, and then you need to look at it differently.
No,
right?
I mean like averaging and averaging is good if you want to do climate prediction over large time scale and spatial scale, but for operational purposes in which you need a prediction of like short time scales and very localized, it might not be as good.
Yeah, I guess it depends on what you average to start with,
Yeah.
right? So if we can gather data sets that are big enough that we have statistical well sample in every condition, then we can average around each of these conditions, I guess. At least it's a bit my ambition, but the question is how huge a data set do we need then to get there? But I agree very much. Thank you very much for your very nice presentation, Luke. And I agree with what you say regarding the damping. And this is the main motivation I have too for getting more and more data. I guess trying to understand if there are different regimes we can isolate and understand if we can make the average on some subset of data and then have something that is more fine grained. That's something exciting to me.
Okay, if there are no other comments, I really hope that this discussion and this seminar will stimulate further collaboration and work well together. Otherwise, please join me in thanking all the presenters and probably see you at the next WISE Zoominar.
Thanks, everyone.
Thank you very much.
Thank you. It was very nice. Thanks.